Okay, yes, class. So we have to start with sharing of capacitors. In the last class, we have completed the energy density portion and the force portion. So how to calculate the force of a capacitor and in this and energy density also. So in this class, we'll be discussing how to calculate the loss of energy in capacitors, and when two capacitors are connected, then what all phenomena occurs. Okay, so I'll be starting with sharing of capacitors in today's class. So firstly, what is meant by sharing of capacitor? You have one conductor, you have second conductor. This is not just specifically for capacitors only, conductors can also be used. When I say sharing of capacitors, it means I'm referring to sharing of conductors too. So it basically means two conductors are present whose voltages are different. One is having the voltage V1, second is having the voltage V2. Now the condition is that V1 is greater than V2. This is the condition. It means V1 has a higher potential and V2 has a lower potential. Now the charges will be moving. Charge transfer will be occurring. The charges will move always from, remember this, higher potential to lower potential. This is the higher potential to lower potential. So till when? Till the time this is achieved. What is this? When both the potentials are same. Potentials are same. Till that time the charges will keep on moving. Till the time the potentials are same. Okay. Now let's see the cases. These are the two capacitors which are present. C1 is the capacitance, V1 is the voltage. Again, C2 is the capacitor, V2 is the voltage. And this is the case before sharing of the capacitors has occurred. Now, how do we calculate the charges? Charge is simply C1 into V1. What is the charge in the second one? It is C2 into V2. What about the energy? Energy is half C1 V1 square. And what is the energy here? Half C2 V2 square. This is the case before they are connected. Now charges will begin to move. Basically, it means that this is going to be discharged. So when it is going to be discharged, look what will be the case. After sharing, the charges will move from the capacitor, which is having the higher potential, towards the capacitor, which is having the lower potential, right? So from a higher potential capacitor to a lower potential capacitor, the capacitors are connected. Okay. I'm audible to you all now?
Yes.
Okay. Now, when the potentials are same, at that time only the charges will stop flowing. So when is that time? That time is when the potential is. So after sharing, the difference that arises is it's just C1 into V. Q2 dash is C2 into V. What is the energy? Half C1 V square. What is the energy? Half C2 V square. Basically, there's a change in the potential only because the potential is same. It's a common potential that is present. Now, what is the case that we have? On connecting the two capacitors, charge flows from one at higher potential to the other, which is at lower potential, until they acquire the same potential. Now, if the charges are just transferring, it means the charges are conserved. Main thing is that the charges are conserved. So if the charges are conserved, it means whatever is the charge before sharing is equal to the amount of charge which is after sharing. So initially we'll be having Q1 plus Q2, and after sharing we have Q1 prime plus Q2 prime. So what was Q1? Q1 was C1 V1. Q2 was C2 V2. And what about Q1? The same common potential which is present is V. So this is C1 into V. What about Q2? C2 into V. This is the case which we have. Now what we can do, C1 V1 plus C2 V2 which is present, C1 V1 plus C2 V2 is present, we can take the common potential common. Capital V can be taken out common from both these values. So V is taken common, C1 plus C2 is present. Now, what is left? What is the value of the common potential that we are getting? C1 V1 plus C2 V2 divided by C1 plus C2. This is how we are getting it. This is the value what we are getting it. And what is this called? This is called the common potential. This is called the common potential. So it is C1 V1 plus C2 V2 divided by C1 plus C. Okay. Write it down, then we'll see the loss of energy. Okay, class. Now let's see the loss in energy. So there was an initial energy which we have seen. There's a final energy which we have seen, right? So when we take the difference between initial and final energy, we get the in energy. Now, why are we considering final minus initial? Reason is that we want the loss in energy. So our answer can absolutely come in negative. Okay, that's why we have taken initial minus final. Now, what was that initial energy? Half C1V1 square. Final energy half C2V2 square. No, sorry. First initial energy of both the capacitors. C1 was half C1V1 square. Second capacitor was half C2V2 square. But then once they were combined, the final energy had the same potential because now the conduction is done and the capacitors have reached the same potential. So half C1V square plus half C2V square. Now this is the loss in energy. Okay, so let's just open up the bracket. So delta U will be half C1V1 square plus half C2V2 square. Let's do one thing. Let's take half V square common. So we are left with C1 plus C2. Now, what was the formula of common potential which we have seen? C1V1 plus C2V2 divided by C1 plus C2. So this is the value of common potential. Let's put it back. So if you put the value of common potential here, you get half C1V1 square plus half C2V2 square minus half. See this C1V1 square, C1V1, right? C1 plus C1, C2. This entire potential's whole square is, look, half C1V1 square, so half C1V1 square. Half C2V2 square, so half C2V2 square. Minus half, C1 plus C2, C1 plus C2. What is left? V square. So we have to square the entire term. So we get C1V1 plus C2V2 whole square divided by C1 plus C2 whole square. Now we can open up this bracket. So the change in energy, this will be C1V1 square. See, LCM will be 2. So this is C1V1 square into C1 plus C2. We have taken the LCM. What will be the LCM? 2 is here and C1 plus C2 is here. So LCM will be 2 into C1 plus C2. Here 2 is already there in the denominator. It means we have to multiply it with C1 plus C2. Here also C1 plus C2. So this becomes plus C2 V2 whole square C1 plus C2. Then see, this is there. Class, this bracket and this will be cancelled already. This bracket will be cancelled. So let's multiply this half and open it. Or this 2 will be taken common. So let's open this. A plus B whole square. So A square, right? C1 square. Plus A square we have plus B square, right? So, but since we have a negative sign, that's why we are writing minus C2 square, V2 square. Clear? A square plus B square. Why minus sign? Because minus sign is there. And we've cut these two brackets. They were same. Now, plus 2AB, A square plus B square plus 2AB. So this becomes minus because of this minus sign. So 2A into B. And this entire term gets divided by 2C1 plus C. Now anything that is being cancelled. Let's do one thing. Let's open the brackets. Let's multiply it with this. Let's multiply it with this. Same thing. Let's multiply it here. Let's multiply it here. Let's open up these brackets also so that whatever things are available common, we can take it as common. So delta U will be, this will be C1 square V1 square plus C1 into C2 into V1 square plus here also C2 C1 V2 square. And what is here? C2 square V2 square minus C1 square V1 square minus C2 square V2 square minus 2 C1 V1 C2 V2. This long portion we have. So divided by 2 C1 plus C. Now see class, things will be cancelled here. C1 V1 square, this will be cancelled. C2 V2 square, they'll also be cancelled. Yeah. So what can we say? A square plus B square minus 2AB, isn't it? This is A square plus B square minus 2AB. Which identity is this? A minus B whole square, right? This is similar to that identity. So let's take C1 into C2 common. So we take C1 into C2 common. So if you take C1 into C2 common, you'll be left with C1 into C2, V1 square plus V2 square minus 2 V1 V2 plus 2 into C1 plus C2. Then we have the change in energy, C1, C2. What is this? A minus B whole square, what we have discussed. So C1, C2, this is V1 minus V2 whole square. Not this, just this individual square, whole square, divided by 2 C1 plus C2. This is the entire formula and the derivation. And this is the loss in energy. Write down the derivation. It's very important. It's very lengthy. And actually, when you will see, you'll see the calculation portion is not very tough. It's just that this is a little lengthy because we have lots of variables, C1, C2, and the entire identities are used. That's why this looks a little lengthy. But when you will calculate, you will see it's not difficult. It's just lengthy. It's not difficult. Write it. Any doubts? Is it clear to both of you? Taha and Sufyan, it's clear?
Yes, ma'am.
Sufyan, it's clear? Sufyan,
Yes.
write it. Yes, class, did you try it? So see, this says that a capacitor of 10 picofarad is charged to a potential difference of 20 volts. It's connected to an identical but uncharged capacitor C2. You have to find the common potential. So these are the values which are given. So what is the formula for common potential? C1 V1 plus C2 into V2 divided by C1 plus C2. So C1 is 10 into 10 to the power minus 12 farad. Voltage is 20. See, pico we have to convert. 1 pico is equal to 10 to the power minus 12 farad. Plus C2 is 10 into 10 to the power minus 12. Voltage is 0. Okay, so this becomes 0 and divided by 2 into 10 to 10 to the power minus 2. So this term will be 0. This is 10 to the power minus 11 into 2, 20 by 2 into 10 to the power minus 11. So this gets cancelled. This is equal to 10. This is the common potential. Second says loss in energy after shearing. So second part, for loss in energy, the formula is C1 into C2 V1 minus V2 whole square divided by 2 C1 plus C. So 10 into 10 to the power minus 11 into 10 to the power minus 11. This is 20 minus 0 whole square divided by 2 into 10 to the power minus 11 plus 10 to the power minus 11. So we can do one thing. We can write this as 2 into not this. So this is 10 to the power minus 11 into 10 to the power minus 11. This is into 400 divided by this. See, this is 2 into 10 to the power minus 11 plus 10 to the power minus 11. Or you can write this again, this denominator part. This can also be written as 2 into 10 to the power minus 11. So 200, 2 into 100, 110 to the power minus 110 to the power minus 11. So this is 10 to the power minus 11 into 10 to the power 2. So 10 to the power minus 9 joules is the energy loss. These are the answers. Write it. Sharing of capacitors is completed. Now we'll discuss one more portion. Write it first. Okay, now there are two conditions which we are going to study. First condition. See, these are two conditions that we have to study, but before that, you should know what is the normal or the original case. All right. So, firstly, when a parallel plate capacitor is present, then in that case, what do you have? What all things do you have? You have a capacitor, right? Capacitor has certain formula, right? Capacitors have certain formula. So the value of the capacitors, the parallel plate capacitors which they have, the capacitance is value. So epsilon naught A by D is present, which is the capacitance which is present. Then the charge is present. Charge is what? Charge is C naught V naught. This is the value of the charge. Then potential difference is there. Then electric field is there. Now, whatever values will be there for the potential difference, it will be exactly for the electric field. Why? Because for the electric field is dependent directly on the potential. So E is equal to minus dV by dr, right? That's why we have this. Now, now let's come to the modifications which I wanted you to study. Suppose the battery remains connected and the space is filled with a dielectric constant. Batteries is connected. So what all changes you are going to observe? Firstly, capacitance is going to increase by K times. K means the dielectric constant, this material which is inserted into the slabs. So this is the dielectric constant which is present. So K C naught. This increases because it is getting multiplied. Then charge is equal to C V naught. Okay, so now capacitance is being multiplied with K, multiplied to K. So charge also increases by K times. This is important, which you have to remember. The two cases where nothing occurs, that is, the potential remains constant, and since the potential remains constant, that's why electric field also remains constant. This is the case when battery remains connected but is filled with fluid. Now suppose the battery is disconnected. This is the disconnection which is shown. So battery is disconnected. So capacitance is K C naught, means it increases K times. Same thing, because it's filled with capacitor. So it is filled with dielectric material, so it is going to increase. What about the charge? This you have to remember. In this case, the charge does not increase. In this case, the charge remains the same. So charge won't change here. Potential didn't change in this in the battery connected one, and charge will remain the same in the battery disconnected one. And what about the potential? Potential decreases by K times. Okay, the potential decreases by K times. And see, if potential is decreasing by K times, electric field also will decrease by K times. This is it. This is a very important portion. You get questions, and more importantly, we'll be starting with the combinations of the capacitor series and parallel. We'll do it here in detail so that we don't have to rush up for the portions which are present in the current electricity. So that time we'll rush up with the resistors. So everything here we are going to discuss it in detail. First, you write down this, make a note point and write down Okay. Uh, done. So let's see one more thing. See, division of charge divides and how voltage divides. So when a charge divides, it divides due to branching. Now see, there's a straight wire here. Charge will move straight. Now if I bend the wire, nothing will happen. Charge will move in the pattern. So I was saying there's a difference between the division of charges and division of voltage. Wire doesn't change the amount of charge. Charges divide due to branching. Now see, this is a straight wire, so charges will pass directly. When the wire is bent, charges will also move in the direction the way wire has been bent. And see, capacitors are added. Nothing happens. Charges will move across it normally and no value deviation will occur. But charge divides due to branching. See, due to this, in this wire, it was a straight wire, capacitor didn't disturb it, so charge was Q. Now branching has occurred. One is Q1, another is Q2. Because of this branching. Now this is the same wire as this of Q1 doesn't divide further. Q1 will stay as Q1. Look, Q2 is still staying as Q2, but here due to branching, the division has occurred. This is how a charge divides. In case of voltage, in a straight wire, nothing occurs. Branching also doesn't affect voltage. See, V everywhere, V. How are voltages divided? As soon as the device enters. On one side of the device, the voltage is different. On the other side of device, voltage is different. Like this is a capacitor, this is a resistor. So on both the sides, the voltages are present and they are different. Like look at this figure. VA, now due to this capacitor, voltages are going to change. The voltage is going to change. So it was VA, now it is VB. So this is VB. And again a device came, so it is V. Also a device came, so it is VD. Like this. This is how voltages will be changing. This is very important. And whatever we have studied for charge, it's exactly valid for current also. This is exactly valid